It's not too bad, right? You know why? Do you know why you find it easy? That's my question for you. Do you know why you find it easy? Anyone? It makes sense. Do you know why you find it easy? Right? This is a lot easier, yes or no? Right? But do you know why you find it easy? Anyone? Yes. Yes, Scott, you know why? Because most of it is from test one. No. Why you find easy? Because sharing stress, okay, is one of the worst. Right? As I told you, right, that topic is difficult to understand. Okay, not difficult. You have so many rules that you have to comply. By the way, sharing stress, I only taught you guys maybe 60% of what I teach in Faculty of Engineering. In Faculty of Engineering, because they have more time, it is a 3 weeks intense course, okay? So they are suffering now, okay? I just finished sharing stress from this because I'm a best teacher, you cheeky sort. I don't think so, okay? I think I'm too passionate, and sometimes when I teach you guys, I feel that I'm teaching my own son or daughter. That's my problem, okay? Too passionate about it. That's why my problem.
So,
I need. Yes,
Professor, could you go back to the example again?
yes.
So, does it matter the point where the maximum?
No. So Kevlar, if I put up here, the answer is the same. I put down here for aluminum is the same. Is the same. Yes or no? Because the
Yeah.
y distance is the same. I just put there. It's just arbitrary points, just to know, let you know where's the y point. Yes.
Yes. Okay. Okay. Thank
Okay.
you.
Okay. Now
And
I'm.
I have just quick
Yes.
question.
Yes.
What if the centroid is the above and then the bottom part is maximum? Then
Yeah. If the centroid is this geometry is what? This geometry is 6, right? If the centroid is, for example, if the centroid is at 2.5, right? So the below distance is what? 3.5, yes or no? Right? So now you focus on the tensile part. Agree or disagree?
oh okay, get it.
Right? Makes sense. Yes? Okay. Next,
Uh,
I'm going to oh, someone have a question.
yeah,
Justin, you
sorry.
okay?
Yeah, just a quick question. So, if the centroid were to end up directly in the middle, so at 3, it wouldn't matter if we went above or below. We just have to say
Yeah,
that it's
but
symmetrical, right?
you're absolutely right. But the thing is, below you don't have aluminum, right? So you also
There.
have to take the top for the aluminum, right? Yes or no? Okay. Now, any other questions before I'm going to add something more. Okay. Some not more difficult, but a bit abstract. Okay. Anyone else? Any question, please? No. Okay. So now, how does this work if you have axial loading? Okay, I want to drive into axial loading also. Is because the next thing that we're going to do, which is eccentric loading, okay, we're going to combine bending and we're going to combine axial load. Okay, so how does it look like? Come on. Okay, so now we are going to do now under axial loading is not so simple anymore. Okay, I mean it's not ridiculous. Okay, so composite material under axial loading. Okay, we are going to do axial loading. Okay, so now, yes, you okay? Okay, I will teach this first before we go for a break. Okay, now look at my transformation. It changes now. Now this is my x, this is my y, this is my rotation in the z direction. Okay, so now what if now? Okay, what if now the material is like this? Now, by the way, at this point, we are not looking at the cross section. I repeat again, at this point, okay, at this point, we are not looking at the what? we are not looking at the cross section. Are we clear? Okay, we are looking at the side view. Okay, look at my transformation. This is not the cross sectional view. Okay, this, I repeat, this is not the cross sectional view. Okay, then we have another material. Okay, so now the material now is under axial load. So 1, 2, 3, 4, 5. So this is under axial load. So P in the X is under axial what? This is under axial loading. Okay, so over here you have Young's modulus of 1, area of 1. Okay, so the area, so over here this has area of 1. Okay, Young's modulus of 2, area of 2. So this is your area of 2. Okay, so this is also a so if we were to view in this way, okay, so this is now my Y. This is a cross-sectional view now. Okay, so this is rotation in the X. Okay, this is the cross-sectional view now. Okay, so this is a cross-sectional view. Right, you'll get it? Okay, so this is E1. This area over here is your A1. Okay, over here is E2. This is area of 2. Okay, so you can see that now. For this case, we have to apply Hooke's law. Okay, we have to apply Hooke's law. So Hooke's law states that stress is equal to E multiplied by epsilon. Okay, so some of you have done your structure and properties of materials. Okay, those of you who have not, what does this mean? So this is strain, this is stress in the elastic region, right? The stress strain curve is straight, just in the elastic region. Okay, so I'll just, out of curiosity, this is your yield. Okay, so this is your Young's modulus. Okay, so Hooke's law is in fact the function of the line. Okay, that here is a relationship stress is equal to E multiplied by epsilon. Okay, so based on material 1 and material 2, right, stress 1 is equal to E1, okay, E1 epsilon 1, okay, and then stress 2, okay, stress 2 means stress acting on material number 2 based on 1 and 2, okay, E2 and epsilon 2. Okay, so now when this thing stretch, now if we put it under load, okay, so let's say now we put it under load, this thing will extend this way. Yes or no? So this is the dotted line I've drawn is the deformation under applied stress or applied force, Px, right? So when that's the case, what you realize that the change in length, right, in reality, the change in length is the same for material 1 and material 2. No change at all. Okay, it's the same. Okay. By the way, that is an assumption that we make. Okay. That's assumption. If you were to ask me, is there changes? Based on geometry, you'll see slight changes. Okay, but in for this case, we're going to assume it be the same. Okay. So for this case, what we will say, so strain is equal to delta L divided by L original. Okay, so where is L original? So when you see from here to here, This is L original. Okay. So from here, we can make the assumption, okay, because they share the same delta L, the change in length, the strain induced in material 1 is equal to the strain induced in material 2. Okay, right? So I'm going to call this equation, I do apologize, okay? I'm going to call this equation number 1. And stress 2 is equal to E2 epsilon 2. This is equation number 2. Okay. So I just showed you, right? Epsilon 1 is equal to epsilon 2 because the change in length for material 1 and 2 are the same. Right? So if the top is the same, the original length the same, epsilon 1 is equal to epsilon 2. Right? So we're going to substitute equation 1 and 2 into epsilon 1 equal to epsilon 2. So what we have, right, is equal to stress 1 over E1 is equal to stress 2 over E2. Okay, so this is the relationship we're going to get. Okay, now based on the so what is Px equal to in general? What is Px equal to? Okay, so we can write the relationship, right? So we know that force, right, P is equal to stress multiplied by what? Area. Yes, right? So for our case, what can we write? Okay, so Px, so therefore, Px is equal to stress A1 or stress 1 multiplied by A1 plus by stress 2 multiplied by what? A2. Right? Okay. So once you have this relationship, right? So once you have this relationship, you can do some manipulating. Okay. So let's look at, I'll call this equation number 3. Okay. So I'll call this equation number 4. Okay. So we're going to let, right, where the first thing we are going to let stress 2 is equal to E2 over E1 multiplied by stress 1. Okay. And this is what I call equation number 5, which is derived from equation number 3. Okay. Right. So I just rearrange this equation over here. Right. That's all I done. Nothing complicated. Okay. So therefore, so we're going to substitute. Okay, we're going to substitute equation number 5 into equation number 4. So what we get now is Px is equal to stress 1 A1, right? Plus, so stress 2 is equal to stress 1 E2 over E1 multiplied by A2. Okay. So I rearrange this. Px is equal to stress 1, right? So we have A1 plus by E2 over E1 multiplied by A2, right? So therefore, the stress in 1, okay, material number 1 is equal to Px over A1 plus by E2 over E1 A2. Okay. So it is not like putting a coefficient anymore. Okay. Now, what if now? Okay. What if now? I'm going to do we'll shortly go for a break. Bear with me. Okay. For less than 2 minutes. Now, what if now we let, okay, we let stress 1, right? Stress 1 is equal to E1 over E2, right? Stress 2. And I'm going to call this equation number 6. And this is also derived from equation number 3. Okay, so I just manipulate this equation over here. Very simple manipulation. Okay, not like your integration. Okay, you guys are going through integration, or your math is much tougher than this, or Laplace transform. Okay, this is Mickey Mouse stuff. The math is Mickey Mouse. The interpretation of the data is different. So we're going to substitute 6 into equation number 4, right? So now we have Px is equal to E1 over E2, right? Stress 2 A1 plus by stress 2 A2. Okay, so exactly the same. So Px is equal to stress 2, right? So this will be E1 over E2, right? A1 plus by A2. So finally, stress into is equal to Px over A1 E1 over E2, right? Plus by A2. The equation, the similar trend, that not the similar trend. One thing that's common is we still apply what? One's Young's modulus over the other Young's modulus. You all see that? Okay. Hey, come on, standardize it. Eugene, write this properly. So this is E1 over E2 multiplied by A1. Okay. So this is, sorry, stress 2. Come on. So this is Px. Okay, this is still Px. This is stress 2. Okay. So this is how, if it's a sandwich material, okay, sandwich material, right, under axial loading, the analysis will look like this. Okay, I mean, I'm just deriving for you guys, okay, to see. Okay, it's not as straightforward as just putting a coefficient down here like bending. Okay, in fact, this coefficient is also a function of what? Young's modulus. Okay, so when you come back, okay, why do I highlight this? Okay, why do you guys say, hey Eugene, this is bending? Okay, why do we do this? When you come back from break, we're going to do eccentric loading. Eccentric loading means what? At point C, where the structure of a fracture will be under both axial loading and what? Bending moment. Okay, so go for a break. Now is what? 10:40. We come back at 10:55. Okay, take a 15 minutes break, and then we carry on. Okay, thank you.